My name is Marina Trevisan from Universidade Federal do Rio Grande do Sul, Brazil, and I'm here to talk about very young galaxies in the local universe. Very deep surveys in the past decades have enabled us to trace the cosmic star formation history from high redshifts to the present. This is shown in this figure of the cosmic star formation density as a function of redshift, where we can see that the star formation density peaked around redshift 2 and declined at later times. If we use this curve to compute the fraction of stars that was formed recently in the universe, we are going to find that less than 2% of the stars was formed in the last 1 gigayear. However, the star formation history of individual galaxies may differ significantly from what is shown in this figure, and it's possible to find galaxies that formed most of their stars at later times. For example, Dressler et al. Found a population of galaxies below redshift 1 that formed at least 50% of their stars within 2 gigayears of the epoch of observation. This figure here shows the fraction of these late bloomers as a function of stellar mass, and different colors indicate different redshift bins. We can see that the fraction of these objects decreases with decreasing redshift, and they effectively disappear at redshift 0. But in the local universe, we still can find galaxies that are very young but less massive than late bloomers. One example is the galaxy 1 Zwick 18, which has a very low metallicity and formed the bulk of its stellar mass within the last 1 gigayear. It can contain a population of old stars, but the star formation rate was much lower in the past compared to other galaxies. The existence of very young galaxies, such as 1 Zwick 18, raises some questions, such as, are very young galaxies frequent in the local universe? What makes Vygs different from others? And what are the mechanisms triggering recent star formation? To tackle these questions, we conducted a series of studies, with the first two being on the frequency of Vygs, and then on the properties and environment of these galaxies. In all these studies, we define a Vyg as a galaxy that formed at least 50% of its stellar mass within the last 1 gigayear. To investigate the frequency of Vygs, we selected a sample of SDSS galaxies at redshifts between 0.005 and 0.12, and we inferred the star formation histories from the SDSS spectra, as shown in this figure. We used 2 different stellar population synthesis codes and 3 different stellar population models. For each galaxy, we interpolated the star formation history and determined age 50, which is the time when the galaxy formed 50% of its stellar mass. This is illustrated here by these red arrows. Finally, we defined the Vyg as those galaxies that have age 50 less than 1 gigayear. One of the main issues when dealing with SDSS spectra is the aperture effect, since SDSS fiber only probes 3 arcseconds of the galaxy. So, to deal with this, we used the global colors, which we computed using model magnitudes, and the fiber SDSS colors. We required that the global colors must be bluer than the fiber colors. Here I summarize the results from our studies on the fraction of Vygs. In this figure, we have the fraction of Vygs as a function of stellar mass for different galaxy formation models indicated by the symbols, and the fraction inferred from observations using 3 different stellar population models. We can see that there is a large discrepancy in both cases, models and observations. And this shows that the Vygs are useful in constraining the uncertainties in galaxy formation models and the stellar population models. Now, given the disagreement that we found between these different stellar population models, to study the properties and environment of Vygs, we selected a, let's say, reliable sample of Vygs by requiring that the galaxy is a Vyg according to all 3 stellar population models. In addition, we selected only objects with high signal-to-noise spectra and with global colors that are bluer than the fiber colors. These criteria lead to a sample of 207 Vygs. And to investigate how Vygs differ from the general population of galaxies, we also selected a control sample of galaxies that have similar redshifts, stellar masses, color gradients, and apparent sizes. Okay, now I will only summarize the quantities that we use to characterize the properties and the environment of Vygs, and I'm going to spare the audience from the boring details of our analysis. We used galaxy colors and star formation rates from the SDSS database. The T-types were taken from the catalog by Domingues Sanchez, and we determined the concentration, asymmetry, and smoothness using the morphometric code. We also determined the oxygen abundances. We retrieved the natural gas mass from the Alpha-Alpha survey, and we obtained the internal extinction from the stellar population synthesis analysis and from the Balmer decrement. To investigate the Vyg environment, we characterized their local, global, and large-scale environments. Their local environment was described in terms of the distance to the closest photometric neighbor, and we also classified the galaxies as interacting and merging system using 3 different approaches. We used the Galaxy Zoo catalog, the classification by Domingues Sanchez, and we also performed our own visual classification. In our visual inspection of SDSS images of the galaxies, we looked for signs of interactions in both the target galaxy and in its neighbor. To determine where Vygs are relative to groups of galaxies, we used the Young et al. Catalog, and to assign the galaxies to these groups, we adopted the assignment scheme from Trevisan et al. We then computed the fraction of Vygs in low and high mass groups, and also determined their position relative to the center of these groups. Finally, we used the catalogs by Temple et al. And Sutter et al. To determine the position of the Vygs relative to filaments and voids. So now, let's jump to the results. We compared the properties and the environment of Vygs with those of the control sample galaxies, and here is a summary of what we find. Vygs are bluer and have higher star formation rates, as expected. The Vyg sample contains 3 times more spheroidal systems compared to the control sample. Besides, the Vyg spheroids are bluer than the spheroids in the control sample. However, despite this difference, the overall distribution of T-types is similar to that of the control sample. Vygs tend to have higher surface brightness, and they are more asymmetric and clumpy than control sample galaxies. The atomic gas mass fraction is higher in Vygs, and they also have more internal extinction. On the other hand, the gas metallicities of Vygs and control sample galaxies are very similar. Regarding the Vyg environment, they tend to be at smaller distances from their nearest neighbor, and they also are twice more likely to be interacting or merging with a neighbor galaxy. Around 50% of Vygs and control sample galaxies reside outside groups, but among galaxies that are residing in groups, Vygs are more likely to be found in the inner parts of low-mass groups. Finally, we do not see any significant difference between the positions of Vygs and control sample galaxies relative to filaments and voids. So, what's the relation between Vygs and other young galaxies like 1Zwick-18 that I mentioned in the beginning of this talk? Well, 1Zwick-18-like galaxies have low gas metallicities, and we do not see that for Vygs. Besides, 1Zwick-18 appears to be isolated, and we see the opposite for Vygs. They tend to have companions. However, it's true that it's very difficult to compare Vygs with galaxies like 1Zwick-18, since we are talking about different stellar mass regimes. In addition, galaxies like 1Zwick-18 are very nearby objects, and it's difficult to determine the global environment due to peculiar velocities. But in any case, Vygs and these other young systems like 1Zwick-18, they appear to be different in nature. And what's the mechanism triggering the recent star formation in Vygs? Well, it's known that wet mergers can induce intense star formation activity, and our results appear to be pointing to this scenario. First, Vygs are more likely to have a close companion, and the fraction of Vygs that have signs of interactions is 2 times higher than that of the control sample galaxies. Besides, they are more likely to be found in the inner parts of low-mass groups, where mergers are more frequent than in clusters or in the field. The asymmetry and clumpiness of Vygs may also be a consequence of mergers and interactions, and higher concentrations too, since mergers can drive gas to the inner parts of the galaxy. The higher internal extinction may also be associated with mergers. These results are in agreement with the models presented in Tweed et al., where they find that Vygs are associated with a recent halo merger. So, our results indicate that mergers are an important mechanism responsible for the intense star formation activity in Vygs. But it seems that it's not the only one, since many of our Vygs reside in the field and they do not show signs of interactions with other galaxies. So, here I leave a summary of what I presented in this talk. Thank you, and you can get in touch if you have any questions.